I had some ideas about the nature of sentience and a leading theory as to where sentience happens in the world. Some people say, oh, you need a brain. Some people say, oh, you need a nervous system. But a major viewpoint, first put out by two fellows from Chile named Maturana and Varela, their theory of what defines life is called autopoiesis. And they define life using this approach that says something is alive that has a bounded structure, that has a porous membrane dividing inside and outside, that there are processes of sensing what's outside, integrating that information, processing it, and then responding. And everything that's alive does that, whether it's a single-cell organism or something as complicated as us or whales or dolphins or elephants, or ecosystems potentially, although whether it extends to a planet, for example, they weren't sure about that. I'm not sure about that, but it's an interesting question. So they said, wherever you find life, you find mind. It's not about a nervous system, it's about being alive. And that even a single cell has a very simple form of mind. Well, the complexity theory work I've been doing, it's all about how groups of interacting individuals self-organize into larger scale structures if they fulfill a handful of simple criteria. And ant colonies are really good ways to explain this. So you need a lot of ants. 3 ants don't make an ant colony. 25 do. If you buy one of those little ant colonies from the back of a comic book, they come with 25 ants. And they build tunnels, and they make food lines, and they even make a little cemetery when ants die that they can put them, which is as far away from the colony and from the food source as possible. And it turns out if you watch ant colonies, 25, they do all these organizational things, but by the time more than half of them have died, they no longer build the cemetery. And then by the time there are 3, they're no longer really doing anything. So you have to have a certain number to get this self-organization. And the more you have, the more complex the self-organization. So 100 ants isn't the same as 1,000 ants, isn't as complicated as a 10,000 ant colony. A village isn't a city, isn't a megalopolis. There have to be feedback loops in the system that are called homeostatic, negative feedback loops. So, like the thermostat in a room. It's set so that the heat comes on until the temperature reaches a certain level, and then when it reaches that, it turns off, and the room cools down then until it gets too cold, and then it gets turned on again. So a negative feedback loop keeps things in a constant range, though it oscillates within that range. Positive feedback loop would be as if the hotter the room gets, the more the heat turns on. And you can have those in complex systems, but they can't predominate. If they predominate, you can get self-organization sometimes, but instead of being adaptive and alive, which is the hallmark of complex systems, instead they're energy expending and self-limited. So you could think hurricanes, tornadoes, economic bubbles, war fever, socially. And for me, from my perspective of applying to cells, cancer is a good example. No ant in the colony is paying attention to whether the whole colony has enough food. So there's no member of the colony is really truly monitoring what's going on at the global level. Some members may think they are, think politicians, but they're often wrong. Though what they're perceiving and how they're behaving can influence the self-organization, but there is no true global sensing. And finally, there has to be a low level of randomness in the system. If there's no randomness, then the system will self-organize always in precisely the same way. So the ant colony will always form the same structures. But then if there's another ant colony that comes in, there's no way for it to find a new way to self-organize in response to that competition. Or if the weather changes and the food source changes, there's no way to change the self-organization to accommodate. But if you have too much randomness, then you don't get any self-organization. So you need this low-level randomness in the system. And this was actually my entry point into complexity, because the early evidence that adult stem cells in humans can sort of be as flexible as embryonic stem cells, which was what my opening salvos in the stem cell world were all about. And that's where a lot of controversy came from, because then you get into the adult versus embryonic stem cell debate. The early evidence showed that this happened. Bone marrow cells, what we were looking at, could become liver cells or lung cells or skin cells, cells of virtually any tissue in the body. But very rarely, unless there's really severe injury of a particular type that would trigger it. So mostly we were finding 1 in 10,000 liver cells, 1 in 1,000 skin cells would be coming from the bone marrow. And at first people sort of rejected that as, well, then it's trivial. So it's not physiologically important. Well, you know, just because it doesn't happen often, if it does happen, it means we can manipulate it, so it's still useful. That was one of my early arguments. But it did raise a question, why is this there? And then I started to realize, once I started learning about complexity theory, oh, this was an example of that low-level randomness in the system. That having that little bit of flexibility meant that when the right challenge to the system came along, it could turn into something more robust that could actually repair tissues. So with the ant colony, from a distance, an ant line always looks like a straight line. But you know, if you bend down and look closely, there's always like 3 to 5% of the ants that aren't following the line. And when I was a kid, these would be the occasional ant that would wander into my mom's kitchen, and she'd be ready to call the exterminator. And if I saw the ant before she saw it, I always felt sorry for it, because I thought, oh, poor, stupid, evolutionarily maladaptive ant who came into the wrong place. You want to be outside, and I would get him on a piece of paper. I was a proto-Buddhist then, I suppose, and I would carry him outside. But she was right, because those divergent ants, if the food source for the food line runs out, it's the ants not following the line that are most rapidly going to find a new food source, like in my mother's kitchen, and establish a new line into her kitchen. So she was actually more adaptive in this situation than I was. So that's what makes a complex system. So we showed that cells fulfill all those functions, and that meant our bodies were self-organizing cells, and not just our human cells. In any human body, estimates are we have 4 trillion human cells, but our body as a whole has about 400 trillion cells. Only 1% of them are human, and the rest are the bacteria that line your skin, all the surface that are exposed to the outside, and all the surfaces inside. So from your mouth all the way out the other end, it's all bacteria. And without those bacteria, we wouldn't survive for more than a few days after birth. The bacteria that line the creases of all your joints are stable, and they're very specific types of bacteria, and they digest the dying skin cells. And when they digest the cell membranes, they create lanolin that lubricates the joints. That's why your skin doesn't crack. And if, as a baby, you didn't have those bacteria, your skin would crack, you'd get infections, and you wouldn't live very long. Your GI tract can't form its structures without the bacteria. The genome doesn't code for the absorptive surface of the interior of the GI tract. It codes for an interaction with the bacteria lining your GI tract, and out of those two things, your absorptive surface is created. So the boy in the bubble, who grows up without bacteria in the environment because their immune system can't handle it, also can't digest food. If you grow a mouse in an environment like that, same thing, but then you put bacteria in their gut, and within days to weeks, they suddenly develop an absorptive surface that allows them to function. So our human bodies aren't functioning human bodies without 100 times more cells that have nothing to do with your human cells. So the body, at a lower level of scale, is like an ant colony made of bacteria and human cells, maybe a few other kinds of creatures, fungal spores perhaps, you know. But mostly it's bacteria and human cells. So cells self-organize into bodies. Bodies self-organize into ant colonies if the bodies are ants. If they're humans, they organize into cities, cultures, political systems, etc. And that immediately implies then that complex systems can exist in hierarchies. So from a distance, I may see an ant colony or a flock of birds, and it will look like a solid shape, a moving shape, but it'll look like a solid thing. And if you ever see a flock of birds from a distance when you weren't necessarily expecting it, you might actually think, what's that thing in the sky? And then you realize, oh, it's birds, duh. But if you don't see what it is, you have to go more closely and observe it, and you see, oh, it's not a thing, it's a phenomenon arising from smaller things. But if you go up to that bird, or that ant, or your own body, and look at it and go, well, this level of scale, my hand looks like a thing, but in fact, it's a colony of cells self-organizing into something that looks like a thing. And when I look at it at the microscopic level, which is what I do all day long at work, is I'm looking at cells at that level. So I'm used to moving between scales like that. Then the body disappears, and it's just a flock of cells, or a colony of cells. So then I had to ask, well, are cells some fundamental unit that are in fact a thing, that can't be at a lower level of scale, that don't dissolve into a phenomenon of smaller things? Well, cells are nothing but biomolecules that self-organize in a watery solution of your body at body temperature. Where do molecules come from? Well, they're just atoms that are self-organizing. Where do atoms come from? Subatomic particles, electrons, protons, neutrons that are self-organizing. Where do they come from? Smaller subatomic particles. Where do they come from? Well, now we're getting down into the quantum realm. No one's really sure what the smallest thing is. The most popular version of that now is strings. That's what string theory is about, the smallest thing. But what physicists do have consensus about is that that smallest thing, there can't be anything smaller. You get down to a level of scale called the Planck Length, which is something like 10 to the minus 37th meters, something like that. So it's very tiny. So where do they come from? Well, they just pop in and out of the vacuum. Now we think of vacuum as being something that's completely empty, but we now understand that the vacuum of outer space or inner space, whatever, isn't completely empty. It's an energy field. And that energy periodically gives rise to mass, because E equals mc squared. And when it does, most of those self-annihilate. So it's sort of like there's this foam of particles or strings or whatever coming in and out of existence. They call that the quantum foam. But sometimes they don't self-annihilate, and then they can interact with other smallest things. And they self-organize into subatomic particles, into atoms, into molecules, into people, planets, galaxies. And so that's the universe. It's just self-organizing complex systems from top to bottom. So this gets us back into consciousness, because Maturana and Varela said life is the smallest unit at which you find this kind of sentience, sensing the world, internal complex processing, and there complex means as in complexity theory. There's going to be some low-level randomness in there, so it's adaptive, and it's not totally predictable because you got randomness. So it's not like an air conditioner senses the environment and responds by cooling the room or letting the room warm up a little bit, because it's not doing internal processing. That's all been set from outside, and there's no randomness. It will always behave exactly the same way, even when completely inappropriate. But living things adapt. Are cells the lowest level of thing that has sentience? And because of this complexity hierarchy thing, I've learned to distrust when anyone says, oh, there's a line here, anywhere in the system. It turns out some biomolecules can do this. The DNA is a perfect conducting wire, with electron flux moving freely up and down the wire, the electrons coming from the base pairs that make up the DNA helix. They dissociate, and you get this current. But because of the shape of the helix, there are electron holes in the flow. So there are places where the electrons aren't flowing. I imagine it like a stream. If you look at a stream going through its little stream bed, there are pockets on the side where you may not get water flowing, or it'll be, instead of getting current, it'll be a little bit still there because maybe there's an obstruction or something. The structure creates areas where there isn't a lot of flow. Turns out those holes are really good for trapping ionizing radiation, which can cause mutations like ultraviolet light. And when it does that, it changes the quantum dynamics of those holes, and they carry the radiation to a different part of the genome. Now, it turns out that most of those holes are over coding regions of the genome, and when they trap the ionizing radiation, they transfer it to non-coding regions of the genome. So you're more likely to get mutations where it doesn't matter than in something that's going to suddenly give you a weird protein and maybe cause cancer or something like that. So there, the DNA helix is behaving like a sentient thing. It's sensing the world, processing it internally, not in a totally predictable fashion, but not totally random either, and then responding in a way that's adaptive. Oh, that's cool. How do higher level organisms do this? Well, we do it through brains perceiving sensation and sensory stuff. Our immune systems are a sense organ, sensing foreign material inside the body and responding to it. Maturana and Varela talked about single cells. Paramecium is a good example. If a paramecium bumps up against a boundary, the membrane will flatten. Calcium channels in the membrane change their shape so calcium can flow in around where the little hairs are that are sort of like the oars that allow the paramecium to swim forward. Calcium flows in, the cilia reverse direction, and it backs up. And then the membrane reshapes itself, the channels close, the calcium dissipates, and then it starts moving forward again. But it's not quite in the same direction, so this is how it gets around a boundary. It looks like it's thinking it through. And what they said is, it is thinking it through, but in a very, very simple way. And it's ions that are carrying that information and processing that information. So in higher level things, we have neurons and immune cells. We have molecules in our bodies like hormones and neurotransmitters that are conveying that information and being involved in the processing. You go down to lower level things, there are fewer things that account for that processing. At the single cell level, it's mostly ions, calcium, potassium, sodium. Exactly the way neurons use calcium, potassium, and sodium to conduct information. At the biomolecular level, it's electrons. Well, okay, if it's down to the biomolecular level, does it go down further? Well, atoms sort of sense the world through their electron shells, and they will respond to that with the quantum dynamics that are how an atom assembles itself, and they will either bond to another atom or repel another atom or just be completely neutral, depending on what it's sensing and how that information gets processed. So there's an even simpler version using electrons as the conveyor of information and the processor of information. Well, let's say you strip away the atoms. Well, protons and neutrons are throwing things like gluons back and forth. That's how they're sensing each other and interacting. Same thing, but simpler. Now when you go deeper, you're back in the quantum realm again, where things get really weird. And there you have non-locality, so that every tiny little particle or string or whatever can be just thought of as a closed little unit. But it can also just as readily be described as a wave function, which extends infinitely to the bounds of the universe. And so every tiny thing overlaps with every other tiny thing. There's no longer inside and outside. It's actually kind of a self-awareness, a self-sentience kind of thing. So according to this model, sentience is actually pervasive throughout the universe. So I discovered at the Stockholm meeting on consciousness not only that I was a synesthete, but I'm something called a panpsychist, which I had no idea what panpsychism is, but I submitted this material as an abstract, and they put me in the panpsychism panel. So I had to go look up panpsychism. And it turns out that people want to say, well, either consciousness emerges from the universe when it reaches a sufficiently complex or a particular kind of organization, like a brain. In Maturana and Varela's autopoietic system point of view, they said, oh, it's not a nervous system, it just has to be alive. But that's still an emergentist perspective, that consciousness emerges when the universe attains that kind of complexity. But using their argument through this complexity theory lens, I can, I think, convert their emergentist perspective into a panpsychist perspective. So that is one way of looking how sentience, in fact, is something that pervades the universe. Wherever you find existence, you find sentience. One of the things that I thought a lot about that's puzzled me for the last couple of years is how could we describe the necessary criteria for whatever that smallest thing is coming out of the quantum foam. Why can it self-organize? Why does it self-organize into larger scale structures that eventually builds a universe? And I really didn't know, I'm not a quantum physicist, I didn't know how to address that question. But gradually I started to think, well, they have to be able to interact with each other. That's the fundamental criterion. If they can't interact with each other, if they don't recognize that the other ones are out there to interact with, to self-organize, complex systems are groups of interacting individuals. That's the minimal criterion. And then when I express sentience in this way, I suddenly realized, oh, sensing the world, internal processing of what has been sensed, and then responding, that's interaction. Sentience is what builds the universe. Consciousness is what builds the universe. Now, sentience is a subset of more complex levels of consciousness like we have, but it's still consciousness. It's just a very simple form. The way these smallest things are a simpler form of what will eventually become a galaxy. So that interests me. I wasn't asking a question about consciousness. I was asking a question about, so what's the structure of the universe? And what does my research have to say about that? And it happened to lead to here. So